You ever get that feeling that your code works, sure, but it isn't exactly smart? Well, that's what we're going to get into today. We're diving into the fundamental strategies that really separate the good code from the great code. We're talking algorithm design. Oh, yeah, we have all been there. You come up with a solution, it gets the right answer, but the second you run it on a big data set, it just stops. The little spinner of doom just keeps spinning, and you start thinking, man, there has to be a better way. And that right there, that's the whole secret. Making the jump from a good programmer to a great one has nothing to do with how fast you can type. It's all about choosing the right strategy before you even write a single line of code. It's about learning to recognize the shape of the problem you're trying to solve. Okay, so where do we even begin with this whole smarter thinking thing? Well, for pretty much any problem you face, your journey starts with the most intuitive strategy there is: good old brute force. Brute force is exactly what it sounds like, right? It's like taking a digital sledgehammer to a problem. You're not looking for clever shortcuts or elegant solutions. You are just systematically trying every single possibility until one of them works. It might not be pretty, but you know what? It's an amazing starting point because it's almost always correct. It gives you a baseline, a score to beat. A perfect example is linear search. I mean, think about it. You're looking for a number in a list. What do? You just start at the beginning and you check every single item, one by one, until you find it. Super straightforward, and hey, it works. But yeah, you can already see the problem. What if that list has a billion items? Yikes. So, how do we get smarter than that? Well, our first big level up is a really powerful strategy called divide and conquer. And the idea here is just, it's beautiful. Instead of trying to wrestle with one massive, overwhelming problem, you just chop it up. You break it into smaller, much more manageable pieces. You solve those little pieces individually, and then you just cleverly stitch their solutions back together. This simple three-step dance is the heart of it all. Imagine you're trying to sort a giant deck of cards. You just split it in half, right? Then you sort each of those smaller piles, and once they're sorted, you just neatly merge them back together. Boom. That's divide, conquer, and combine. It's the whole idea behind famous algorithms like merge sort. All right, let's switch gears. Our next strategy is a little different. It's all about making the best decision you can right now and just hoping it all works out in the end. This is the greedy approach. Think of a greedy algorithm like you're hiking with a compass but no map. At every single fork in the road, you just pick the path that seems to point most directly toward your destination. You're not thinking about the whole journey, just the very next step. This makes it super fast, right? But you can probably guess the problem. Sometimes that direct path leads you right off a cliff. This approach works great for certain kinds of optimization problems, like scheduling. Let's say you've got a list of possible activities, each with a start and end time, and you want to cram in as many as possible. A really effective greedy strategy is to just always pick the activity that finishes the soonest. You do it, you commit, you move on. And for this particular problem, it's actually the perfect solution. But not all problems are that straightforward. Sometimes the little pieces you break a problem into, they aren't independent. They affect each other. And for those tricky cases, we've got to open up the expert's toolkit. We're starting with a technique that's both incredibly powerful and, honestly, a little dangerous: recursion. Recursion. It's this idea where a function literally calls itself to solve a tinier version of the same puzzle. And man, it can lead to some of the most beautiful, elegant code you'll ever write. But it also comes with a massive warning label, and you're about to see why. Let's look at a classic example, the Fibonacci sequence. Now, this recursive code, it looks perfect. It's so clean, it basically is the mathematical definition. You want the fifth Fibonacci number? No problem. Just ask for the fourth and the third. Simple, right? Well, here's the trap. Just picture the chain reaction this sets off. To get fib 5, it calls fib 4 and fib 3. Okay, but then to get fib 4, it has to call fib 3 again? We're literally doing the exact same work twice, and it gets so much worse. The entire chunk of work to calculate fib 3 gets redone from scratch over and over. The amount of wasted effort just explodes. So that brings us to a huge question. One that leads to maybe one of the most powerful strategies out there. How do we keep the beauty of recursion, but get rid of all that crippling, repeated work? The answer is dynamic programming. And the core idea is so simple, it's brilliant. Don't solve the same problem twice. That's it. You calculate something one time and you save the answer. The next time you need it, you don't recalculate, you just look it up. And this is where you can really see the difference. It's just night and day. It's the difference between constantly redoing work and just remembering. The naive recursion is like running the same 100-meter dash a dozen times. Dynamic programming runs it once, writes down the time, and then just refers to the notepad. It's a total game changer. And finally, in our expert toolkit, we've got a strategy for when the journey is the destination. It's called backtracking. The best way to think about it is like you're in a maze. You pick a path, you follow it, whoops, hit a dead end. No big deal. You just backtrack. You go back to the last place you made a choice and you try a different path. It's the perfect approach for puzzles like Sudoku. All right, we have gone through a lot. So let's pull all of this together into a handy little cheat sheet, something you can use to guide your own thinking when you face a new problem. Now, don't just see this as a summary. Think of it as your mental flow chart. Always start by asking yourself, okay, for real, can I just brute force this? If not, move on. Can I split this problem into clean, identical smaller pieces? You're looking at divide and conquer. Can I just make the obvious best choice at every step? That smells like a greedy algorithm. Wait a minute. Am I solving the exact same subproblem over and over? That is a giant flashing neon sign that says, use dynamic programming. And finally, do I just have to explore a bunch of different paths until one works? That's a job for backtracking. So look, if you take away just one thing from all this, let it be this. Before you write a single line of code, just stop. Take a breath, look at the problem, see if you can recognize its shape. Choosing the right strategy first is, without a doubt, the single most important thing you can do to write truly smart and efficient code. And this quote just nails it, doesn't it? Because this stuff, it isn't just about making your code run faster. These are mental models. They are tools for thinking that help you take a messy, complex problem and give it structure. Because when you learn to see these patterns, you're doing more than just becoming a better programmer. You're becoming a better problem solver, period. So the next time you're staring down a tough challenge, don't let your first question be, how do I code this? Instead, ask yourself, what kind of problem is this really? Trust me, the answer to that question, it changes everything.